This is joint work with Tobias Fiebig from TU Delft, Shuang from UT Dallas, as well as my two advisors, Christopher Kruegel, as well as Giovanni Vigna from the University of California, Santa Barbara. Rather than talking about hardware attacks or looking at essentially the actual terminal, as we've seen in the 3 previous talks, I'm actually going to talk about stuff that happens more at the application level. And specifically, I'm going to motivate all of this by something that I'm sure a lot of you will essentially feel related to, and specifically looking at Uber, which I'm sure a lot of you are using to essentially get from the airport to an actual conference like NDSS. And specifically, what Strife is doing is trying to protect you from essentially IP address takeover attacks, where somebody is able to take over an IP address that you might have been previously using, and which then might have domain names. In this case, for example, the SAO static.uber.com domain, which pointed to an IP address which was previously in use by Uber, but then was freed, and nobody actually ever cleaned up that specific domain name, which ultimately resulted in people being able to get your cookies from basically once you've logged in into the Uber website. So you log in into Uber, you go to, in this case, saostatic.uber.com because somebody might lure you into it, or because some resources are included from there, and because of the way that Uber was distributing cookies, they were suddenly able to get your cookies for the Uber website and suddenly impersonate you to Uber, get a ride, take your credit card information, all of this. And the reason that this is happening specifically is because you might have a domain, for example, cloudstrife.seclab.cs.ucsb.edu, which might point to an IP address, in this case, for example, 34.215.255.68. And if you're actually trying this right now, it still points to it, but that IP is not actually free. And the question, of course, now becomes, if you don't actually use the host behind that IP address anymore, because, for example, it might be an IP that's part of an EC2 instance, and you're actually freeing the EC2 instance on Amazon because you don't want to pay for it anymore, the question now becomes, how are you going to migrate DNS gracefully? Are you first going to remove the DNS name, and then you're freeing the IP address? Or are you doing it the other way around? If you're doing it and you're first releasing the domain name, are you then going to wait until the TTL, so the time which your record can be cached, is actually timing out? Are you doing this later? Are you doing this immediately? The reason why you might actually want to wait longer is because some recursive name servers in the middle might actually cache entries longer than what the TTL is specified at. So this is particularly the case for name servers in, for example, China, which might cache records for up to a day, even though your TTL is actually set to 60 seconds. And then you similarly have a similar problem if you, for instance, are on EC2 and you have automatic scaling, and somebody might throw a denial of service attack at your system, and you're shutting down your instance, and you're starting a new one. This then, by default, means you're getting a new IP address. You might automatically have the DNS records point over, but recursive name servers might still have old records cached. And this is becoming a problem because by having this and combined with domain-validated certificates, somebody is able to actually impersonate a URL and actually get, for example, secure cookies. In the case for Uber, for example, of course, the cookies were only transferred via HTTPS. Uber, of course, set the correct header to only transfer cookies if it's not via plain HTTP, because otherwise somebody could just take them if they're essentially, for example, man in the middle. And the reason why domain-validated certificates are a problem here is because somebody can just, to some degree, claim that they're having access and are owning this domain. And generally, domain-validated certificates are a good thing. We want to keep them. They're credited for the rise in HTTPS adoption. They're usually free. For example, if you look at Let's Encrypt, it basically skyrocketed in adoption in general. So starting basically from January 2017, it is since then the most famous, not necessarily famous, but the certificate authority with the largest market share. And the reason why HTTPS-based domain validation is a problem, because it acts only as a proxy that you actually own the domain. So what it actually does is, it actually just verifies that you control the host behind a specific domain. So if Uber, for example, forgets to remove the domain name entry from saostatic.uber.com pointing to a specific IP address, and you can get that specific IP address, then now, by proxy, you can prove ownership of that domain, even though you're not actually a legitimate owner of it. And this works by you as a user actually just going to a certificate authority, telling them, it's like, hey, I would like a certificate for example.com. The certificate authority for example, Let's Encrypt, or others like Komodo, for example, might just tell us, okay, this is a challenge. This is a challenge you should post on your specific website. So they're telling you, hey, take this and post it on your website. You're doing this, so you're taking the challenge, you're putting it at example.com, and then at a later point, the certificate authority goes there, makes sure that the random nonce that you should be putting there is actually there. And so as I told you, this means that if you can control the host that is behind a specific domain, you basically prove ownership of this domain. And this is, as I said, by proxy, because it's not actually true. You're not actually owning the specific domain. You're just controlling the host behind it. And once you've done that, you can actually use this for a variety of nefarious purposes. You might want to get a TLS certificate, which is trusted. If you're using Komodo and you have a little bit of money to spare, you even can get a certificate that's trusted for 3 years and is a wildcard certificate. It costs you around $1,200, which you might want to use later for man-in-the-middling on a Wi-Fi access point to impersonate it in different ways. If the domain is still included in other websites, you can now use it to inject malicious code. In the case of Uber, you might want to launch a subdomain attack to steal cookies. If there's no MX record for a specific domain, then suddenly you can receive and send emails from that domain because based on the SMTP standard, it falls back to an A record. Similarly, you can exploit residual trust in a specific domain for spam or phishing. So I think every one of us would probably trust an email that comes actually from saostatic.uber.com more than something that has a random domain name. The question, of course, now becomes, is this generally a problem that is occurring on the internet? Is this a problem at scale? So what we decided to do is we decided to look into this a little bit more. So specifically, we looked at, are there any active domains that are pointing to IP addresses that I, for example, could just ask for or get? And specifically with active domains, what we mean is domains that somebody is trying to actually resolve. So somebody is trying to send a DNS query for it, and we are seeing that DNS query. And that is data that we're collecting from Farsight. So Farsight is helping us essentially get through and figuring out which active domains, so which domains are actively being resolved, which point to free IP addresses. And to make this a little bit more tractable on our part, we're limiting ourselves to cloud IP addresses. And the reason here is that cloud IP addresses are the ones that are the most ephemeral, are the ones that you can get the easiest. You don't have to go somebody in person and ask them, hey, can I get the IP address to point so that I can control it? But rather, you just go there and say, like, hey, give me an IP address, give me an Amazon EC2 instance, give me a Microsoft Azure instance. And once you've done that, you essentially get IP address and you can churn through all of them. And that's exactly what we did. So over a period of 1 month, we allocated one IP address every 2 seconds on every single availability zone for Microsoft Azure as well as Amazon EC2. And if you do this with a very short or small allocation cycle of one IP address per 2 seconds, then you're churning through entire address pools in usually around a day, but always in less than 2 weeks. And we then correlated this looking at how many domains on the internet point to IP addresses in cloud providers which might be free. And there are 130 million domains that we've got over a period of 120 days that are pointing to cloud IP addresses. And over 700,000 of them can readily be taken over by an attacker. And an attacker doesn't actually need to wait 2 weeks, but an attacker can do this within a few minutes, and in some cases, even within a few seconds. And the reason why an attacker can do this so much more quickly is because, of course, he is not bound to have to do this with only one IP address every 2 seconds, but if he's hitting the rate limiting, in this case of EC2, for example, he can allocate 10,000 IP addresses per second and free them. There's some eventual consistency issues that might reduce this in practice, but still, it's a significant amount of IP addresses that you can get and then churn through. So what we need to do is we kind of have to assume that these takeover attacks can and will happen in the future. And at the same time, we can't really do any major changes to the DNS deployment. If anybody who's tried to do that, I'm sure has at least a few years of failure trying to actually get something deployed there. So we need to try to prevent this abuse or these attacks at a higher level. So we decided we're going to focus on services that are based on TLS. Because with TLS, we have a trust-based ecosystem that we can rely on. So if we can leverage the certificates that exist to protect it, that would be great. And for some protocols, there's ways that you can protect this already. And the simple idea for HTTP, for example, is you start with just getting a trusted certificate. You're going to enable HTTP strict transport security, which means as soon as somebody has been there with HTTP once, after that they'll always be using HTTPS. And then you just pin the certificate that you have, right? Your certificate. The problem here is, in this case, your takeover attacks are going to require a PIN certificate, which an attacker cannot get because, well, you have the certificate that is pinned to. So effectively, you're reducing any takeover attack to denial of service attack. The problem here is this doesn't really work for SMTP, IMAP, or a lot of other protocols that use TLS because they don't have the concept of public key pinning generally. And in fact, if you think about this a little bit more, it doesn't even work for HTTPS because public key pinning is actually going to be deprecated by Chrome because too many people shot themselves in the foot by essentially throwing a denial of service attack at themselves by limiting to the wrong public key. And similarly, as I mentioned before, once you lose the public key pinning, it gets significantly easier for an attacker because, well, he only needs a domain-validated certificate, which he can use. And he can simply get this from, for example, Let's Encrypt or Komodo. So we've decided we need some kind of better idea. Particularly, our idea was then, OK, let's start with the same set of goals, basically, and the same set of steps that we want to take. But now, how about we're preventing certificate issuance when we think that a domain has likely been taken over? And this then also works in the cases where we might have SMTP, because if an attacker can't get a certificate and there's certificate checking by the client, well, then there's no connection. But the question now becomes, how are we going to actually prevent that certificates are being issued? So how can we detect that a domain or the IP address behind the domain has actually been taken over? And this is where, fortunately, certificate transparency logs come into play. So generally, certificate transparency logs are public append-only logs where every certificate that has been issued is going to be published. And as a user, you're incentivized to actually check that a suspicious certificate might have been shown up. In itself, however, certificate transparency logs are reactive. So you first have to check whether a certificate has been issued. So it doesn't actually prevent a certificate issuance. So which means as you as a domain owner, you have to check is there a certificate? If it has been, you have to suddenly go to the certificate authority that issued the certificate, request it to be revoked, and hope that all of the clients that would connect to your service actually check revocation, which I'm sure many of you know is not actually happening. However, if you think about this a little bit more, you could actually move the check not to the user, but have the check happening at the certificate authority and use this as, to some degree, historic lookups. And that is exactly what we're doing with HTTP, preventive domain validation. And it works the same for the end user. So the end user still goes to the certificate authority. It's going to check, like, hey, I would like to have a certificate for example.com. But now, rather than immediately returning it like, here's the challenge, the certificate authority is first checking, OK, does there a previous certificate exist for this domain that is currently still valid? And based on that knowledge, it then might respond with a different challenge. But assuming that there is a previous certificate, then now it responds with a challenge, hey, you need to host this at the HTTPS URL rather than straight HTTP. You as a client simply host it there, and the certificate authority then later verifies it. And the only additional requirement that we have is that if there's an old certificate that has been found, then we require that it's actually being used for signing the HTTPS request. So basically, the only thing that we're requiring is that when you want to renew a certificate or you get a new certificate, and there's currently still one that is valid, then you have to use the old one to actually show that it works. And by doing this, we're effectively preventing the TLS certificates are going to be issued through HTTP-based domain validation in cases where there is a domain takeover. And this then means that takeover attacks are basically significantly less useful because you don't have a certificate anymore, nobody is connecting to it. You're still getting the benefit of a denial of service attack, but at least you're not impersonating anybody anymore, and you cannot steal cookies. And the only drawbacks that you have for legitimate users is if they break the chain of trust from the existing certificate to the next and the new certificate. And this only basically happens in disaster recovery scenarios where you suddenly lose the key, or if you are actually giving up the domain. But then you can rely back on more thorough domain validation techniques. For example, asking you to change entries in the domain, in the actual zone of your domain, which you can only do if you actually own it. And ultimately, we actually proposed this to the ACME v2 working group of the IETF, which have been so far fairly receptive, and we're currently working on getting an RFC drafted to that as an additional challenge for ACME v2. And with that, I would like to thank you for your attention, and I'm happy to take any questions.
Yeah, hi, Matt Ford, Internet Society. This is great work. Can you say any more about the status of getting this progressed in the IETF? You said they've been receptive, but are we? When are we going to see an RFC and an implementation of Let's Encrypt, for example?
So we're not sure when we see something from Let's Encrypt. So we are hoping to get an RFC out until hopefully the next IETF meeting, which I think is in July, so that we can then discuss it at possibly ACME v2 working group sessions. But like generally, we don't have an exact timeline. There's also the historic lookups are also a thing that, of course, need more attention, essentially, to do this like efficiently and getting certificate transparency logs in a way that you can actually look them up in a way that is tractable for certificate authority. And then we're hoping to get this through the CA browser forum in a way that's actually recommended for CAs. And once we are at the stage where one CA at least has adopted it, I think we're going to be fairly soon to the point where most CAs would adopt it because users could restrict CAs through CAA records on the DNS level.
Thanks. The next IETF meeting is next month in London, actually. But
yeah, I don't think we're going to make that.
Hi, Ben Stock from CISPA. I was wondering, can you give me an intuition? She said 130 million domains could have potentially been compromised. Are we talking about Alexa top million? Are we talking about random domains? Did you characterize these domains somehow?
We did not characterize them. So a lot of the domains, I'm sure, are going to be primarily low traffic rather than, but at the same time, if you look at cases, for example, the Uber example, where sao-static.uber.com is generally a low traffic domain, but the impact of the vulnerability is really high, right? Somebody can steal all the session cookies of people who are logged in. And none of the domains, so all of the domains that we've seen traffic for are actively being resolved. So there are at least some people always looking on, like trying to actually access.
But maybe there's bug bounties in that for you if you look at the data a little bit further.
Yeah, we haven't done yet.